Welcome to my online course in linear algebra for undergraduate mathematics. In this lecture, we are going to discuss matrix of linear transformation. If T from U to V be a linear transformation where U and V are finite dimensional vector space over the field F, B1 equal to U1, U2 up to N be a basis of U and B2 equal to F1, F2 dot Fm be a basis of V since each G image of EI belongs to this V. So, and B2 is a basis for B. Each GEI can be expressed as the unique linear combinations of the element of the vectors in B2 as given in this GE1 is equal to alpha 1 1 F1 plus alpha 1 to F2 plus alpha 1 M Fm. TE2 is equal to alpha 2 1 F1 plus alpha 2 2 F2 plus alpha 2 M Fm goes on TEN alpha N1 F1 plus alpha N2 F2 plus goes on alpha N M Fm. Now the matrix representation of T is defined in this way: T E in the suffix E and in the power it is half given by coefficient in the expression of coefficient in the right hand side of the expression of TEI transpose, and this is equal to alpha 1 1 alpha 2 1 goes up to alpha n 1 alpha 1 to alpha 2 to alpha n 2 alpha 1 m alpha 2 m alpha n m. Next is example on matrix of linear transformation. First question: let T from R2 to R2 be a linear operator given by T x1 x2 equal to minus x2 x1. Find the matrix of T with respect to order basis. Order basis are also known as standard basis. Here standard basis for R2 is 1 0 0 1. Given Tx1 equal to minus x2 x1 and standard basis of R2 is 1 0 0 1. So T image of 1 0, the basis element are T of 1 0 is my 0 1. Express this 0 1 in terms of this, that is 0 into this element plus 1 into this element, I will get 0 1. Again T image of 0 1, T image of 0 1 is my minus 1 0, expressed minus 1 0 in terms of these two elements as standard basis of R2 is this one. So minus 1 into this element plus 0 into this element as given by this. Therefore, the required matrix of T with respect to order basis is the transpose of the coefficient matrix in the expression of the T image of 1 0 and T image of 0 1. Coefficient in the right hand side of the expression T image of 1 0 T 0 T image of 0 1, that is 0 1 minus 1 0 transpose, and it is equal to 0 minus 1 1 0. Take another example. Determine the matrix for linear transformation T from B2 to B3 given by T x1 x2 is equal to x1 plus x2, 2 x1 minus x2 7 x3 with respect to his standard basis. Given T x1 x2 equal to x1 plus x2, 2 x1 minus x2 7 x2. We know that the standard matrix for P2, standard basis for P2 is 1 0 0 1 and V3 is 1 0 0 0 1 0 0 0 1. Now T image of this element as this is the basis for P2. T image for first element 1 0 is 1 2 0, putting the value of 1 0 here in the given linear transformation. I will get 1, here it is 2 and here it is 0, that is 1 2 0, and express this in terms of this basis element, that is 1 into first basis element 1 0 0 plus 2 into second basis element 0 1 0 plus 0 into third basis element 0, 0, 1. Again, find out the t image of this element 0, 1. That is, here it is 1, here it is minus 1, and here it is 7. Again, express this 1 minus 1, 7. In terms of this element, we will get this one. This one. Therefore, required matrix of T with respect to the ordered basis or standard basis is the coefficient in the right hand side in the expression of T10 and T01. That is, yeah, it is 1, 2, and 0. Then 1 minus 1, 7. Transpose of this matrix is 1, 1, 2, minus 1, 0, 7, which is the required matrix. Third question, let V be a vector space of polynomial in X over the field F of degree 3 and 1x x square x cube is a basis for V. Find the matrix of differentiation transformation D from B to B relative to the basis 1x x square x3. Here linear transformation is my differentiation transformation D from B to B. So find out D of 1, that is first basis element, which is equal to 0, and express this 0 in terms of this basis element for the polynomial of degree 3, that is 0 into 1, 0 into x plus 0 into x square plus 0 into x cube. Then again take the second basis element D of x, which is equal to 1, that is differentiation of x is equal to 1, and express this 1 in terms of this basis element, that is 1 into 1 is 1, and put 0 in front of this coefficient, that is plus 0x plus 0x square plus 0x cube. Again take differentiation of x2, that is twice x, and express this in terms of the basis element, that is 0, 1, 0 into 1 plus 2 into x plus 0 into x square plus 0 into x cube. Again take differentiations of the last basis element, that is x3. This is equal to 3x2. Then express this in terms of basis element, that is 0 into 1 plus 0 into x plus 3 into x square plus 0 into x3. Therefore, required matrix of D with respect to the basis for the polynomial of degree 3, that is this basis, we have this one. That is transpose of the coefficient of the expression for the differentiation of 1x x square and x cube. This is equal to 0, 0, 0, 1, 0, 0, 0, 0, 0, 2, 0, 0, 0, 0, 3, 0. Take the transpose, which is equal to 0, 1, 0, 0, 0, 0, 2, 0, and 0, 0, 0, 3, 0, 0, 0, which is the required matrix for the given differentiation of node transformation. Next is algebra of linear operators. Let T1, T2 be 3 linear operators on V, and I from B to B be a identity map given by I of P is equal to B for all B. Clearly I of P is a linear transformation. Then following conditions hold. That is I into T, identity mapping into the linear operator T is equal to T, and it is equal to T into identity map I. T within bracket T1 plus T2 is equal to T1 plus T2, and T1 plus T2 T is equal to T1 T plus T2 T. For any scalar alpha, T1 T2 is equal to alpha T1 into T2 is equal to T1 alpha T2. Fourth property, T T T T T T1 T2 is equal to T1 T2. This property is known as associative. This is distributive property, left and right distributive. This is now for any V belongs to V, IT is V image of IT is equal to I into TV. From the definition of identity mapping, this is equal to TV. Similarly, we can show that T I V is equal to T I image of V. Since I image of V is V, this is equal to TV. Therefore, IT is equal to T, then it is equal to TI. Okay. Next, take the left hand side of the 2, that is T of T1 plus T2, X image of T1 plus T2, which is equal to T within bracket T1 plus T2 image of X. Then using the property of linear transformation, this can be written in this form T within bracket T1x plus T2x. So again use the property of linear transformation, I will get this one. T1x, T2x, and this can be written as T1x, T plus T2x. Again use the property of linear transformation, I can write 8T1 plus T2x. Similarly, we can show that T1 plus T2 into T is equal to T1T plus T2T. Now third property, for any scalar alpha, alpha T1, T2 x is alpha T1, alpha, keep alpha outside, then T1, T2 x. Again by definition of the linear operator T1, T2, this is equal to alpha T1, T2 x. Then take alpha T1, T2 x. This can be written as alpha T1, T2 x. Then take this alpha outside as it is scalar. This is a T1, T2, T2x. Again T1 alpha T2x can be written as T1 alpha T2x, and this is equal to T1 alpha T2x. As alpha is scalar and T1 is linear operator, we can take alpha outside, and this is T1 T2x. From hence we can get the equality as right hand side are equal, so left hand side is equal. That is alpha T1 T2 is equal to alpha T1 T2, and it is equal to T1 alpha T2. Fourth property, T of T1 T2 hex can be written as T1 T2 hex. That can be written as T1 T2 hex. Again T1 T1 T2 hex can be written as T1 T2x. This can be written as T1 T2x. As right hand side are equal, left hand side are also equal, hence we get the equality. These are your home assignment. You should solve this one. In case of any query, question, doubt, you can ask me. Next Thursday, there will be a doubt clearing session. You should come to the college, clear your doubt. With that, your third unit is completed. Remaining will be the next lecture. Thank you.